Hello everybody and welcome to this course on partial differential equations. This is the first session of my course. Here we introduce partial differential equations and how to form a partial differential equations from the given conditions. So you will learn how to form a partial differential equation by eliminating arbitrary constants. PDE stands for partial differential equations. How to form a partial differential equation from the type phi uv equal to 0, where u is a function of xyz, v is a function of xyz, and z is a function of x and y, and how to form a partial differential equation given a geometric condition. Now, given a function of two or more variables, an equation involving one or more partial derivatives of a function is called a partial differential equation. So, what is a partial differential equation? It is an equation involving one or more partial derivatives of a function. For example, given del z by del x plus y equal to 0, there is one partial derivative with respect to x. d2z by del x squared is del z by del y plus z. Again, there are two partial derivatives. And here z is the dependent variable. Z is a function of x and y. If each term of the partial differential equation contains either the dependent variable or one of the partial derivatives, then the partial differential equation is said to be homogeneous. So what is a homogeneous differential equation? It contains either a dependent variable or one of the partial derivatives of the dependent variable, every term. For example, del z by del x plus del z by del y equal to 0. Both terms have dependent variables, so it is of degree 1, order 1 and homogeneous. d2z by del x del y is xy. This term does not have a partial derivative, so it is non-homogeneous of order 2 and degree 1. Degree 1 because this is of degree 1. d2z by del x squared is del z by del y plus 2z. Again homogeneous, every term has either z or partial derivatives of z. Its order 2, degree 1. Degree is the order of the highest derivative. d2z by del x squared plus d2z by del y squared equal to 0. Again homogeneous because each term has a partial derivative, order 2, degree 1. If z equal to fxy, there are some notations you need to know. Del z by del x or zx you denote by p. Del z by del y or zy you denote by q. d2z by del x squared I denote by r, that is zxx. zxy is d2z by del x del y I denote by s. And d2z by del y squared is zyy, which I denote by t. Coming to questions. Form the partial differential equation by eliminating arbitrary constants. So I have 2z equal to x squared by a squared plus y squared by b squared. So we have to eliminate a and b. So first differentiate this partially with respect to x. So I get 2zx is 2x by a squared. So I have zx is x by a squared, or zx is p is x by a squared, or a squared is x by p. Now the equation is 2z is x squared by a squared plus y squared by b squared. Differentiate partially with respect to y. So I get 2zy is 2y by b squared, or zy is y by b squared, or q is y by b squared because zy is q. So b squared is y by q. Now we have to eliminate the arbitrary constants. So this is your equation, 2z is x squared by a squared plus y squared by b squared. These are the values of a squared and b squared. Substitute them here. So I get 2z equal to x squared, x and by p here, plus y squared y by q. So simplifying, we get 2z equal to px plus qy. So this is the required partial differential equation formed by eliminating the constants. Question 2. Form the partial differential equation of the family of all spheres whose centers lie in the plane z equal to 0 and have radius r. So this is given a geometric condition. What is a geometric condition? All the spheres which have radius r and whose centers lie in the plane z equal to 0. So let the center of the plane be AP0. Z coordinate is 0 because it lies in the plane z equal to 0. So your equation of the sphere becomes x minus a the whole square plus y minus b the whole square plus z minus 0 the whole square, that is z squared equal to r squared. So differentiate with respect to x first, so I get 2x minus a plus 2z del z by del x is 0 because z is a function of x and y. So when you differentiate with respect to z, I get 2z del z by del x. Or x minus a is minus zp because p is del z by del x. Again we have x minus a the whole square plus y minus b the whole square plus z squared equal to r squared. Differentiate partially with respect to y. So I get 2 into y minus b plus 2z del z by del y is 0. Or y minus b is minus zq because q is del z by del y. So we have coming back to our original equation, x minus a the whole square plus y minus b the whole square plus z squared equal to r squared. Substitute x minus a as minus zp, y minus b as minus zq here. So you get minus zp the whole square plus minus zq the whole square plus z squared equal to r squared, or z squared into p squared plus q squared plus 1 equal to r squared, taking out z squared. This is the required partial differential equation. Question 3. Find the partial differential equation of z equal to e raised to y f of x plus y. Here f is a function of x and y. So first take partial derivative with respect to x. So I get del z by del x is e raised to y f dash x plus y, or p equal to e raised to y f dash x plus y. Again z equal to e raised to y f of x plus y, differentiate partially with respect to y. So we get del z by del y is q. We have to apply product rule here. So it is e raised to y, first keep it outside, into f dash x plus y, derivative of x plus y is 1 with respect to y, plus f of x plus y e raised to y. So q equal to e raised to y f dash x plus y, z is nothing but f of x plus y e raised to y, so it becomes plus z. Or q minus z is e raised to y f dash x plus y. So we have these two equations, p equal to e raised to y f dash x plus y and q minus z is e raised to y f dash x plus y. Dividing one by the other, we get p by q minus z is equal to 1. So p equal to q minus z is the required partial differential equation. Now given a partial differential equation of the form phi uv equal to 0, where u is a function of x, y, z, v is a function of x, y, z, and z is a function of x and y, we apply the chain rule, that is del phi by del u into del u by del x plus del phi by del v into del v by del x is 0, and del phi by del u into del u by del y plus del phi by del v into del v by del y equal to 0. That is a chain rule. So form the partial differential equation phi xy plus z squared into x plus y plus z equal to 0. So phi is a function of two variables u and v. So let u be xy plus z squared, v is x plus y plus z. So coming to the chain rule, we have del phi by del u into del u by del x, which is plus del phi by del v into del v by del x is 0, or we have taking this to the other side, del phi by del u into del u by del x equal to minus del phi by del v into del v by del x. Now phi uv equal to 0. Again, so we have del phi by del u by del y plus del phi by del v by del y equal to 0. This is second equation in the chain rule. So I have del phi by del u into del u by del y is minus del phi by del v into del v by del y. So these are our two equations which we got. So we divide 1 by 2. So what happens? You have del phi by del u gets cancelled, del phi by del v gets cancelled, and I get del u by del x by del u by del y is equal to del v by del x by del v by del y. Now what is del u by del x? It is x plus 2zp. Del u by del y will be x plus 2z del zy, that is q. Del v by del x is y plus you're differentiating with respect to x. So it will give you 1 plus p, and del v by del y will give you 1 plus q. Because del v by del x is 1 plus del z by del x is p, del v by del y is 1 plus del z by del y is q. So we have this equation, y plus 2zp by x plus 2zq is 1 plus p by 1 plus q. Cross multiply, then you open up the bracket, so I get y plus qy plus 2zp plus 2zpq equal to x plus 2px plus 2zq plus 2zqp. So 2zpq gets cancelled, shift everything to one side. So I get y minus x plus qy minus 2zq plus 2zp minus px equal to 0. Or I get y minus x plus q into y minus 2z plus p into 2z minus x equal to 0. So this is your partial differential equation. So you have learned how to form a partial differential equation by eliminating arbitrary constants using a given geometric condition, and also how chain rule is used. You have seen. Practice along with me every step, every line. Only then you can master this topic or any topic in maths. Thank you and see you in the next session.